What are KE Jetronic systems? If you know KE Jetronic systems, you're well on your way to understanding KE, also known as CISE, brought to you by Bosch. The E means electronics added to CIS, improving starting, drivability, and throttle response. The KE Jetronic system looks like K, but the fuel distributor is different. KE Jetronic systems provide limp-home operation as a mechanical-type continuous injection system. To know which cars have KE, on the fuel distributor, look for the pressure actuator, sometimes called the electro-hydraulic actuator, or the differential pressure regulator. In this program, you'll see how the KE control system, the air system, and the fuel system function together to meet different driving conditions. First, the KE air system looks much the same as K. Intake air deflects the sensor plate according to airflow. That airflow is controlled by the throttle. Here's one big difference. In the zero position, an O-ring seal supports the KE plunger when the engine is off. There must be clearance to the roller so the plunger can rest on the O-ring to seal line pressure. In zero position, the wire clip supports the sensor plate. In the basic position, the roller just touches the plunger. It's important the sensor plate can move a few millimeters from zero before touching the plunger. Any further movement lifts the plunger off the O-ring seal. The clearance shows in this updraft KE air funnel. Below the funnel is a straight cylinder section shown by the two lines. In the zero position, look for the plate near the bottom of that cylinder. When it's lifted to the basic position, look for it near the top, where the funnel meets the cylinder. In updraft sensors, you lift the plate from zero to basic. In downdraft airflow sensors, you push down from zero to basic. Also in KE downdraft, the sensor plate and cylinder are at an angle. You'll want to know downdraft-updraft differences when checking for clearance. The KE fuel pump accumulator and filter are about the same as K. System pressure is shown in red, return in yellow. The KE pressure regulator maintains system pressure, returning fuel to the tank. Besides controlling system pressure, it also controls return from the fuel distributor, the thin yellow line. It looks different from K, and it's outside the fuel distributor. Look for the thinner return line from the pressure actuator to the regulator, yellow arrow, and the system pressure inlet, the red arrow. When the engine is turned off, the pressure regulator quickly drops pressure, shown by the graph, so the injectors close and seal. Residual pressure is held by the accumulator in all the lines shown in orange. Check the circled points if you have a hot start problem or if the system won't pass the leak test. In some cars, you'll find air-shrouded injectors. Through an air passage from upstream of the throttle, air is drawn in around the injection spray through the plastic insert. Air-shrouded injectors atomize the fuel better, improving economy and emissions at idle. Also, air-shrouded injectors stay cooler. You may stop now to review the air system, also the fuel system. In CIS metering, the airflow applies up force to lift the plunger, which opens more of each slit. The more the slits open, the more fuel passes through. From here on, KE Jetronic systems get really different. On the KE plunger, the downforce is system pressure, which is constant. So for any given airflow, plunger lift is constant. In K, reducing control pressure allows the plunger to rise to open the slits and increase fuel delivery for the same airflow. Depending on the opening, fuel at system pressure flows through the slit into the upper chamber at reduced pressure, shown in purple, and flows out to the injector. That's what we call injected fuel. For any airflow and slit opening, KE mixture can be compensated by changing pressure in the chambers. We'll look at that important idea a step at a time. how pressure changes affect the flow of injected fuel, and how the actuator changes pressures in both chambers. In a separate path, what we'll call actuator fuel flows continuously at system pressure in red to the pressure actuator. It flows at reduced pressure, shown in purple, through the lower chamber. The restrictor is a small orifice that determines the rate of through flow, shown in yellow, as it returns through the pressure regulator to the tank. These two different fuel flows, injection fuel above and actuator fuel below, are separated by the diaphragm. Notice the KE diaphragm is spring-loaded from below, the opposite of K. The pressures are related. When lower chamber pressure is reduced, the diaphragm moves down to reduce upper chamber pressure accordingly. To enrich, more injection fuel flows when the pressure drop is greater at the slit. It's easier for fuel to get through. Pressure drop is increased by increasing the difference between system pressure and lower chamber pressure. That's sometimes called pressure differential. To lean, less injection fuel flows when the pressure drop is less. It's harder to get through. Fuel flow to the injectors depends on the pressure drop, the difference between system pressure and chamber pressure. The greater the difference, the greater the flow. Pressure drop of injected fuel at the slits is controlled by pressure drop of actuator fuel. The pressure drops in the circles are related. Pressure drop at the slits can be changed by changing pressure drop at the inlet to the actuator. Let's look at the next step to see how the pressure actuator for any given airflow and its related slit opening compensates mixture by changing flow of injected fuel. The actuator valve is made small so it can move fast to improve drivability. In this disassembled part, actuator fuel comes to the inlet at system pressure. When assembled, the plate can be pulled toward the inlet to reduce the pressure of the inflow. The plate is controlled by a small electromagnet. More magnetic force pulls the plate closer to increase pressure drop by restricting the inflow. Less magnetic force allows the plate to rise to decrease pressure drop. Using a digital meter, you will be measuring the small current, in this case 10 milliamps, that operates the electromagnet. It's important that you realize that 1 milliamp is 1/1000th part of 1 ampere, and milliamp currents like this are adversely affected by oxidation on connectors. You may stop now for review of magnetic force and metering by pressure drop. See if you can put it together. For typical warm engine operation, the valve is pulled close to the inlet with about 10 milliamps. This causes a small pressure drop between system pressure and lower chamber pressure. The drop on the gauge is about 4/10 bar. Injected fuel flow through the slits is normal. To lean the mixture, the plate is allowed to move away at reduced current, perhaps only 1 milliamp. The pressure drop is only 2/10 bar, so injected fuel decreases. To enrich, as in warm-up, the plate is pulled closer with more current, say 70 milliamps. Pressure drop increases to 1 bar, so injected fuel increases. More current means more pressure drop, means more fuel injected. When you've got that, you've got the basic idea of KE Jetronic systems. To cut off fuel injection, such as during coasting, current is reversed to move the plate completely away from the inlet. With no limit to the inflow of actuator fuel, system pressure is in both chambers, so the spring pushes the diaphragm up, closing the outlet and cutting off injected fuel. When you pull the connector, the warm engine runs, but runs leaner than with a typical 10 milliamp actuator current. That represents a limp home condition. Think about how changes in pressure drop of actuator fuel are caused by changes in magnetic force, resulting from current change. and how that pressure drop can be seen on the gauge. How the related pressure drop at the slit changes flow of injected fuel. You may stop now for review. Mixture control depends on variations in pressure drop. In this section, you'll put the theory to use. KE mixture control depends on inputs from sensors, including ignition circuit for engine speed, oxygen sensor, engine temperature sensor, throttle switch for closed and wide open throttle indications, and a sensor special to KE that signals movement of the sensor plate. These inputs go to a digital electronic control unit. Outputs control mixture and, in most cars, operate an idle speed stabilizer to govern idle RPM. First, let's see how KE Jetronic systems control mixture to suit different engine operating conditions. When the key is turned to start, three things happen. One, as soon as the starter turns the engine, the control unit turns on the pump to build system pressure. Some cars also have a pre-supply pump. The control unit operates the pump safety circuit through the relay and the ignition circuit. If the engine stops turning for more than 1 second, as from an accident, the control unit shuts off the pump, even with the key on. Here's the second thing that happens with the key in start. The control unit sends more current to the pressure actuator for start enrichment, lasting about 1 second. Cold start needs more enrichment to the port injectors, so the plate is pulled close to the inlet by this maximum current, typically about 150 milliamps. This causes maximum pressure drop at the inlet and at the metering slits. Third thing, the key powers the start injector. It's grounded by the thermotime switch, just as in other Jetronic systems. But if your KE car does not have a thermotime switch, the start injector is powered through the control unit. For post-start enrichment, increased actuator current keeps the engine running right after starting. Then, enrichment tapers off during warm-up, depending on temperature. You can see the importance of the engine temperature sensor. Be careful not to confuse it with the thermotime switch or any other sending unit. The temperature sensor is called NTC, negative temperature coefficient, because at shop temperature its resistance is higher than it is when the engine is warm. As a result of this input during warm-up, compensation changes from cold, more pressure drop from more milliamps, causing more enrichment. Changes as current cuts back gradually during warm-up until it reaches normal warm engine conditions. Part throttle acceleration considers economy and emissions, adding just enough enrichment for good drivability. For a warm engine, it's handled just like KE Jetronic systems. But for a cold engine, the KE sensor plate potentiometer signals how fast the sensor plate moves as airflow increases and how far it moves. From this input, the control unit sends a compensation output to the pressure actuator. For about 1 second, current increases, depending on sensor plate movement and on engine temperature and RPM. That's important for drivability of a cold or cool engine. Full throttle enrichment is different, calling for maximum torque without regard to economy. A throttle switch signals full load condition. Depending on that full load signal and on RPM and engine temperature, the control unit adds about 3 milliamps to compensate the mixture for full load acceleration. On cars with RPM limitation, signals from the ignition circuit cause output as reversed current, minus 40 milliamps in this case, to protect the engine from overspeeding. With current reversed, system pressure is present in both chambers, so the spring pushes the diaphragm up to cut off injected fuel. The same thing happens in cars using coasting cutoff. When the throttle switch signals the throttle plate is closed, depending on RPM and on engine temperature, reversed current to the actuator cuts off injected fuel. When does coasting cutoff not operate? Not with a cold engine, not at low RPM to prevent stalling, not when shifting a manual transmission, and not while in cruise control. In some cars, an altitude sensor causes signals to reduce fuel delivery when the air is thinner. If your car is much above sea level, the altitude sensor may be signaling for a leaner mixture. Time for a brief review of lambda. The lambda symbol describes the air-fuel mixture, ordinarily about 14 parts of air to 1 part of fuel. The engine runs rich, lambda less than 1, when the mixture has more fuel than can be burned with the air. The engine runs lean, lambda more than 1, when the mixture has more air, when air is left over after all the fuel is burned. Operating right at lambda 1 is important for emission control. So lambda 1, 14.7 to 1, is normal for warm engine, part throttle operation. In some cars, the oxygen sensor is heated electrically, powered from the fuel pump relay circuit. Getting hot sooner improves drivability and reduces emissions. As you recall, this sensor samples the oxygen content in the exhaust. When it's hot, the system operates closed loop. The sensor generates about 1 volt when the mixture is rich and should be changed toward lean. The sensor puts out low voltage when the mixture is lean and should be changed toward rich. During normal operation, voltage signals fluctuate, averaging small changes in the mixture to stay close to lambda 1. As sensor voltage changes back and forth, lambda signals from the oxygen sensor are input to the control unit. The output signals the pressure actuator. Here is closed-loop fluctuation, from 8 milliamps increasing to 12 and decreasing to 8. In these pictures, exaggerated for clarity, the plate is always moving slightly toward the inlet and away from it, changing the pressure drop slightly, the result of changing current to the pressure actuator. With engine warm, with oxygen sensor hot, look for actuator current to change back and forth in a narrow range. Closed-loop fluctuation is normal, averaging to maintain lambda 1. In open loop, oxygen sensor disconnected, engine warm, actuator current should be about the middle of the fluctuations and as specified. When you see no change, you know the system is open loop. You may stop now for review of mixture control by actuator current. If idle adjustments are necessary, KE mixture is adjusted according to 2 specifications: milliamps to the pressure actuator and CO readings on the exhaust gas analyzer. Besides adjusting mixture, you may adjust idle RPM when the engine has an auxiliary air valve. But when the engine has an idle speed stabilizer, as on most KE Jetronic systems, turning the idle speed screw will not change idle RPM. Here's why. The idle speed stabilizer controls RPM by changing the amount of air bypassing the closed throttle. Idle RPM is programmed in the computer and cannot be changed. Shapes may differ, but they work the same. The cutaway shows the blade, which changes the opening for this flow of bypass air. For normal warm engine, the bypass is partly open. The bypass closes somewhat to reduce RPM, and it opens to increase RPM. That's why it's called an idle speed stabilizer. That's why turning the idle speed screw will not change RPM. Idle speed inputs include RPM, closed throttle switch, engine temperature, and sometimes air conditioning. To run at the set RPM, the control unit sends digital on-off signals to the idle speed stabilizer, specified as % dwell. In some cars, the air conditioning system signals the stabilizer to raise RPM for better compressor output. During cold start, the control unit sends more dwell, longer pulses to open the stabilizer, adding extra air to bypass the closed throttle. Idle specifications are given in dwell for a specified RPM. In summary, you've seen the KE Jetronic system differences from K. In the air system, if you can feel proper clearance, that is, if you can move the plate as specified from 0 to basic position, that ensures the plunger is seated on the O-ring seal to hold residual fuel pressure. The pressure regulator also handles return of actuator fuel from the lower chambers of the fuel distributor and holds residual pressure when the engine is off. The valve controls inflow of actuator fuel. More magnetic force from more current means more pressure drop, which means more injected fuel. For part throttle acceleration, the sensor plate potentiometer signals movement of the sensor plate. You've seen the inputs to the control unit and changing outputs of actuator current that compensate mixture by changing injected fuel for each operating condition. And you've seen the inputs that control idle speed on KE Jetronic Systems, brought to you by Bosch.